welcome back to the lectures on Subrimanian geometry. So we've been talking about the Heisenberg group. Our preferred model for the Heisenberg group is R3 with the product law, this one here, which we saw that makes the left invariant, which makes left invariant the vector fields that we consider, call it X and Y. So the reason why this is a good model is because it canonically identifies the group with its Lie algebra. In other words, we're working exponential coordinates. So all this terminology of Lie groups will be clarified later. So don't worry if you're not following. I'm telling you why there is something more important behind this model. Okay. However, from what we saw also before, because of this uniqueness of the Heisenberg structure, all the models are actually equivalent via a smooth group morphism. So, in other words, we are considering a three-dimensional space with three vector fields, X, Y, Z, and with the property that X bracket Y is Z, and Z commutes with X and Y. And okay, it's a fact that actually there is a group structure on R3 that makes these three vector fields left invariant for the group structure. Okay. Now, what we do, let me recall how to define a subRiemannian structure from these vector fields. In our model for the subRiemannian Heisenberg group, we have the vectors. We have x, that is dx minus y over 2 dz. We have y equal dy plus x over 2 dz. And we consider the subbundle of the tangent bundle delta such that the fiber at every point is equal to the span of the two vectors x at P and y at P. And then we set it a smooth curve. Gamma is horizontal, it's called horizontal. If the derivative of the curve lies in the span of the vectors, so it lies in this subbundle for all t. For all t. In other words, there exists for every point of time t, there exist two numbers I1, I2 of t, such that gamma dot t is equal u1 t x at gamma t plus u2 t y at gamma t. Okay, another name for horizontal is Legendrian. Now, if we have a horizontal curve, so if gamma dot t is equal to u1 t x gamma t plus u2 t y gamma t, then we define the length of gamma is defined as the length of gamma is the integral over the domain of the curve gamma of the square root of u1 t square plus u2 t square root in dt. Which is the same as saying that we are declaring x and y orthonormal. Now that we know how to measure the length of horizontal curves, we define the Carnot-Karateodori distance. Karateodori distance. That is, so the distance CC stands for Carnot-Karateodori between 2 points P and Q is the infimum of the length of gamma, such that gamma is a horizontal curve and goes from P to Q. Another name for the Carnot-Karateodori was contact distance. But the term Carnot-Karateodori is more general because it will be constructed in higher dimensions as well. Now, R3 equipped with this distance function is the subRiemannian Heisenberg group. I will open a parenthesis to explain you why this distance is adapted to the group structure. In other words, the geometry was invariant under the left translations of the group structure, and therefore left translations acts as isometries with respect to this distance. Okay, let's clarify what I mean. Okay, let's remember that R3 has a group structure that makes X and Y left invariant. We already did this calculation, and we know that this means that for every element of this group, if I left translate the vector field and then I evaluate at a point, then I exactly have the vector field evaluated at the left translation of that point. So maybe it's better to put here differential the translation at the point P. The analog for Y. Left translation Y at P is equal to Y at the left translated point. Okay. Now what it says, first of all, it says that if gamma, so if gamma is horizontal, so it's horizontal, and we write x dot equal to u1 x compose gamma plus u2 y compose gamma, then the left translation of the curve, now this is a new curve, I claim that this is also horizontal. And what is the derivative of the curve? So the derivative over the t of Lg compose gamma t, this is just the differential of the left translation at the point gamma of t applied to the vector gamma dot of t, which is, since the curve is horizontal, I can write it as differential Lg gamma t of x u1 forgot u1 x compose gamma plus u2 y compose gamma. Now this is fixed t, right? So now u1 and u2, these are scalars, right? So they go out. This differential is a linear map, so I can split the sum, I can remove the scalars, so this is equal to u1 dlg gamma t of x compose gamma plus u2 dlg at gamma t of y compose gamma. Okay, so but now we have that this vector field is the vector field x at the point g of gamma t. Right? So we continue. So we're calculating the derivative of Lg compose gamma at t. So what we have now u1 times the vector field at the point. So it's u1, the vector field at the point. Of course, can only be at the point where the curve is. So it's the g gamma t plus u2, similarly, right? Gamma g gamma t. Which is the same as saying is like u1 x at the curve Lg compose gamma t plus u2 y Lg compose gamma t. So we prove that this curve is horizontal. Moreover, the multiple of tangents that you need to write in the basis xy for its vector, they're except again u1 and u2. So the length of the curve g gamma Lg compose g gamma, this is again is the integral of u1 square plus u2 square root integrated, which was exactly the length of gamma. What we have said is that each left translation preserves horizontal curves and their length. But now, if we go back and we look at the definition of the subrimanian distance, the Carnot-Quadratic distance, we see that if you left translate a curve from P to Q, you left translate by G, then you have a curve by GP to GQ. It's still horizontal, has the same length. And remember, then we can apply the same reasoning to the inverse of the left translation, which is the left translation by the inverse, which what we understand, so the conclusion is that there is a correspondence between the curves that are horizontal from P to Q and the gamma, or let's call it maybe sigma, that are horizontal from GP to GQ, that preserves the length. Therefore, for every G, the distance, so if we infimize the curve, the length of the curve between P and Q, we obtain the same thing of infimizing the curve from GP to GQ. In other words, left translations are isometries. The space is isometrically homogeneous. Every point can be sent to any other point by a left translation.
Back to our space.
This space is three-dimensional, so we can draw pictures of of the curves that are reaching the infimum and the spheres, the metric spheres. So we will draw a lot of pictures. So let's start. Let's go in that direction. So we're going to discuss the geodesics and the spheres in the Subrimanian Heisenberg. Okay, now it's better if we recall how we constructed this Subrimanian structure and how we constructed the bundle, the tangent subbundle in the picture in the back. This will help us using the geometry of the planar curves to understand the geometry in the Heisenberg structure. So let's say that we have a curve in 3D. So it has 3 coordinates, and let's call it x t, y of t, and z of t. Then, so the first thing is gamma is a horizontal curve if and only if the curve satisfies the following differential equation. Z dot is equal 1/2 of x y dot minus y x dot. In other words, this is how you write the fact that the tangent vector of gamma annihilates the contact form, or which is the same as saying that gamma is tangent to the subbundle delta. And we got to that equation because what we imposed was that the curve zt is the spanned sine area of the planar curve x, y is up to time t. So, recall, so we had zt was the integral from 0 to t of the of 1/2 x y dot minus y x dot. And we're interpreting this as the sine area of the curve. Okay, good. Now, what about the length of the curve? So whenever you have a horizontal curve, so gamma dot is equal to u1x gamma plus u2y of gamma. Now, look at this fact that, so x dot is, y dot is, gamma dot is x dot, y dot, c dot, okay? On the other hand, x is 1, 0, main coordinate is minus y over 2. Or maybe instead of y, we should put the second coordinate of gamma. Okay, it was y, so this is y of t. And the other one was 0, 1, x over 2. So you see, this equation now tells you what are u1 and u2. So what we have that u1 is equal to x dot and u2 is equal to y dot. Okay, so now what about the length? So gamma horizontal implies that the length of gamma, which is by definition the integral of u1 square plus u2 square, is the same of the integral of x dot square plus y dot square. And what is this? This is equal then to the length of the projection of the x of the curve xy. So this is the Euclidean length of the planar curve t goes to xt yt. Very good. So summarizing, so the horizontal length, I mean the length of horizontal curves equal the length of projections of those curves on the plane. Because of the previous discussion, we will obtain explicit formulas for the geodesics in the subRiemannian Heisenberg group by using the fact that we know the solution of the isoperimetric problem. So I'll put some infos about the isoperimetric problem in the description of the video here below. So in fact, so we now know that for how the geometry in the Heisenberg group has been constructed, that the shortest curve with respect to this length structure are the lifts of solutions of a variant of the isoperimetric problem. Namely, we search for those curves on the plane that enclose a fixed area and join two given points. We shall see that such curves are arcs of circles or pieces of lines, and therefore the geodesics in the Heisenberg group are lifts of circles. So we want to prove the following proposition. So fixed the endpoint of a curve, fixed x1, y of 1, z of 1 should be the endpoint of a curve in 3D. The curve, the planar curve, x of t, y of t, that encloses sine area z of 1, so this point here, and such that starts from the origin, so x of 0 is equal to y of 0 is equal to 0, and that minimizes the Euclidean length of the curve is an arc of a circle, an arc of a circle, or a piece of a line. After we will have this, then as a consequence, length minimizing curves, okay, from the origin, so from 0, 0, 0, in the subRiemannian Heisenberg group, are lifts of those, are lifts of circles or lines. Okay, so now let's explain why this is true, and then we will lift the curves and get all the geodesics. So, as I said, this is a consequence of the isoperimetric problem. So, proof. So, I will draw a lot of pictures now. So, let's say that, so I'll draw the projection in the plane. So we have 0, 0, And then we have a point that is x of 1, y of 1. Okay, and now we look for a shortest curve enclosing area Z. Okay, so first of all, let's consider the straight segment between these 2 points. And now what we want is that the curve here is going to enclose area C of 1. So now let's do like this. Let's consider first the arc of the circle. Okay, so I will draw the picture again. Let me draw the picture again. So we consider the segment. Let's say that we have I don't want to make it symmetric necessarily. Okay, so this is the circle. So let's say the sigma is the circle such that the area below the line is Z of 1. Okay, so this area equal Z of 1. So only this part here. Okay, maybe one. Okay, it's one should really actually differentiate the two cases in which Z1 is 0 and one is non-zero. Okay, the case of Z1 is equal to 0, then it's easy. Okay, maybe let's do that first and then we can go back. So if Z1 is equal to 0, then the straight line from 0, 0 to x1, y1 is the shortest curve between them. Okay, so between them, so these 2 points, I mean, okay? And this curve encloses area 0. So it's also satisfying this condition automatically, okay? In particular, it is the shortest with the extra requirement Z equal to 0, right? So it's clear, right? So we have the origin, we have the point x, y, then we take this straight segment, and then this curve here encloses area 0. Right? You can either write with the formulation, with the integral formulation, or really see that the area is fine by this curve, enclosed by this curve, and the straight line to itself back. So this encloses 0 area. So when Z is equal to 0, Z1 is equal to 0, we solve it, and that's the curve. Okay. Now what about if Z1 is non-zero? Okay, it's either positive or negative, but it's very symmetric. Let's think that Z1 Z1 is positive. Otherwise, we have to go orient the circles in the opposite direction. So if now we orient the circle in this way, then what we know is that these curves, so we took the arc of the circle that encloses area Z1. So I really want to prove that this is the shortest curve. Okay, so I complete this curve to a circle. Okay, now what do I know? I know that this circle is the best, is one of the best. It's that encloses that given area. Okay, so this area, so let's call this area A, and this area will be B, right? So A and B will be just the area of the circle. Okay, now let's assume that we have another curve. Okay, let's call it tau. Tau is another competitor. So it's a curve that goes from 0 to the point x1, y1, and encloses area z1. So also this area here, it's equal to A. So this is A. Okay, and now what we understand that this curve, now following tau plus this other piece of the circle, is a curve that encloses area A plus B. And it's another closed curve. Okay? So let's say that this was below was sigma, and this is sigma, no, let's call it eta. So we have that sigma followed by eta is a circle. If I consider now tau followed by eta, then this is a closed curve, enclosing area A plus B, which is the same as sigma followed by eta. But now what do we know? We know, therefore, that this curve, tau times followed by eta, cannot be shorter than the circle that encloses the same area. Okay? By the solution of the isoperimetric problem, the curve tau followed by eta is a circle, but it's a circle that coincides with another circle on some interval, then must be a circle. Okay, or in other words, even if this were 0, we didn't have it, then this piece has to be a circle. Okay, so this implies that by the isoperimetric solution implies that tau is a is not, so if it was a different curve, is not shorter than, no, it's really shorter. So it's really longer, strictly longer if it is different. So let's make it clear. So it's another competitor with tau different, even up to reparameterization, than sigma. Then tau is strictly longer than sigma. And this completes the proof. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on Subrimanian geometry, please subscribe to the channel clicking below. Bye.